Welcome again, ladies and gents, to another flipped lesson. Our theme of the day, understanding what this word stoichiometry means. What stoichiometry allows us to do as a chemist is to mathematically quantify the relationship between the reactants and the products in a chemical reaction. So we want to start thinking of these reactions as like our recipes in chemistry. Just like when you bake cookies, you follow a recipe. It tells you need so many cups of flour plus some sugar, milk, and other things to make your batch of cookies. These chemical reactions are the recipes of chemistry. They tell us what products we need to put in to get, what reactants we need to put in to get a desired product out. So the reaction we're going to be working with today is making ammonia, which is this guy right here. We can use him as a household cleaner. So this is kind of a really good thing that we need. So what this reaction tells us is three different things. The first thing we can look at is how this reaction deals with particles. So if I'm looking at the reaction, what my coefficients tell me is that one molecule of N2 gas needs to react with 3 molecules of H2 gas in order to make 2 molecules of NH3. So my recipe tells me how many molecules of each thing I need to put in order to get my desired amount of product out. So that's the first way we can think of our reaction. The second way we can think of our reaction is in terms of mass, because all chemical reactions follow the law of conservation of matter, and that's why we balance them. In order for our reaction to be perfect, we have to have the same number and types of atoms on both sides of the reaction. That way we know that matter is conserved. So what that means is if I put a total of 2 grams of my reactants in, I need to get, I want an equal sign there. I need to get a total of 2 grams of my products out. Because since my matter is conserved, it's not going to be created, it's not going to be destroyed. So if I put a total of 2 grams of my reactants in, I'm going to get a total of my 2 grams of products out. And we'll talk a lot more about this as the week goes on. But the most important way that we as chemists think about our chemical reaction is in terms of moles. We learned this guy last week. So we learned that 1 mole is how we count in chemistry, because that mole equals 6.022 times 10 to the 23rd particles. So we can go ahead and we can count using this number. So if I know I have 1 mole of something, I've got 6.022 times 10 to the 23rd particles. If I have 2 moles, I have twice as much. If I have half a mole, I have half as much. So this is the way that we can count particles in chemistry. And we can also relate moles to these chemical reactions, because these coefficients tell us how many moles we have of each piece of our reaction. So if I'm looking at this guy here, what this also tells me that 1 mole of N2 needs to react with 3 moles of H2 in order to get 2 moles of NH3 out. So this is probably the most important application that we have for this reaction, is the idea of understanding that those coefficients tell us how many moles of each piece we have. Because what that allows us to do is it allows us to calculate and manipulate how much product we can get from a certain amount of reactants. So for example, if I didn't want to make 2 moles of this, if I wanted to make 4 moles of my ammonia, I know that I need to double how much N2 and H2 I put into that reaction. So we can use our skills of dimensional analysis to go ahead and calculate that way. So if we look at this reaction, here's our problem. How many moles of ammonia, NH3, are produced when 6.0 moles of N2 reacts with hydrogen? So if we look at this reaction, there's a couple of important things. One, it tells us we want to go ahead and calculate how many moles of ammonia we can get. It tells me that I'm putting in 6 moles of N2 and then I'm reacting it with hydrogen. What this tells us is that we have more than enough hydrogen for this reaction, so we don't need to worry about it. So the only pieces we care about is the link between how much N2 we put in and how much NH3 we get out. So we can go ahead and we can set up a dimensional analysis problem. So we want to know how many moles of NH3 we can get when 0.60 moles of N2 is reacted. So what we can do is we can use these coefficients as a conversion factor. In my problem, I know that 1 mole of N2 gets me 2 moles of NH3. So I can set that up across my conversion factor just like we did with our mole map in the last chapter. So I'm going to use my coefficient in front of my NH2, which is 1, on the bottom, so my NH2 moles cancel. So 1 mole of N2 goes on the bottom, and I'm going to put my NH3 on top. So 2 moles of NH3 goes on top. My moles of N2 cancel, so I'm left with moles of NH3, so I'm going to go ahead and just multiply on my calculator. I do 0.6 times 2 divided by 1, so it's just 0.6 times 2, which gets me 1.2 moles of NH3. So when my 0.6 moles of N2 reacts, I can make 1.2 moles of NH3. On your Google form, I'd like you guys to go ahead and give me the answer to this problem here. Notice there's blanks in front of it, which means it's not balanced. So make sure you balance it first before you go ahead and try and answer the problem. And as always, if you have questions, please put those in the form so I can address them at the beginning of class. Hope you guys have a great day, and thanks for stopping by.